Hello, Chemistry 11 Honors. This is Mr. Chan. And today what I wanted to do was continue on with the simple gas laws notes that you received last day. Now, there is one section, it says gas law stoichiometry example. At this point in time, I just want you to skip this particular section because of the fact that I will talk about it in another section. But I do want to talk about Dalton's law of partial pressures. Dalton proposed that in a mixture of gases, each gas expands to fill that container. And in that expansion, each gas exerts the same pressure called partial pressure that it would if it were the only gas present in the container. So if we were to take a container and we were to take the total pressure of that container, what we do is we take the pressure of gas A plus the pressure of gas B plus the pressure of gas C and add them all together. Just like if I were to ask for the total age of students in the class, I would take the age of all the students in grade 10, age of all the students in grade 11, and the age of all the grade 12s in the class. Now, one thing we can do here is we can derive from here the percent of pressure for gas A would be equal to the pressure of gas A divided by the pressure of all the gases added together. Okay. Now, one thing about this manipulation of the formula, it is related to something called the mole fraction, okay, where the mole fraction is the moles of substance 1 divided by the total number of moles. Now, what you can do is you can refer to your textbooks, and I believe if we take a look on page 205, 206, what you can see is you can see what they talk about for partial pressures. Okay, 206, 207. And I believe if you look further down on page 207 and 208, they give you the derivation of how mole fraction is related to partial pressures. So if you take a look on page 207 and 208 in your zoomed out text, what you can see is you can see the derivation or how these two formulas are related. Now, if you take a look, continue to take a look on page, let's see here, we have 208. What they do is they give you some sample questions on page 208 and then 209, okay? And they give you something special on page 210. Now, if you take a look on page 210, one thing that you need to be aware of is they talk about something called, the vapor pressure of water. Now, here, if you take a look on page 210, they talked about, in this particular case, oxygen was collected by the displacement of water at a total pressure of 754 torr. Now, why did they use the word total pressure? Okay. Because what happens is when you collect something over water, what you have to do is consider the pressure of the vapor produced by the surface of the water. This is touched upon on page 209. Okay. So it says here, a mixture of gases results whenever a gas is collected by the displacement of water. So you take a look at this little section on page 209, and they mention the term vapor pressure of water. So in this particular scenario, when you're considering the total pressure of something collected over water, what you need to do is not only consider the pressure of the gas, but you also have to consider the pressure that's produced by the vapor coming off water. Okay, so in this case, This is why in the question, you see here, it says the volume, the vapor pressure of water is 20 at 22 degrees Celsius is 21 torr. So what happens is when you look at the total pressure here, not only is it the pressure of the gas, but also it's the pressure from the water vapor to give you 750 torr. And that's why they had to do a correction before they were able to find the number of moles of oxygen gas. All right, that's just something I would just touch upon while we're talking about partial pressures. Okay, now, another thing that we should touch upon is something called Graham's law. So what is this Graham's law? Is the rate of effusion or rate of diffusion of a gas is inversely proportional to the square root of its molar mass, which we give the symbol m. So basically, you can think of it, the smaller the molecule, the faster the rate in which that particular molecule diffuses or effuses. Now, in this little diagram, you see the difference between diffusion and effusion. Diffusion is where you remove the barrier and the particles can spread out by itself, while effusion, what you have is a pinhole leak or a pinhole for the gas particles to go through. So what is the formula for this? So what you have is the rate of gas 1 divided by the rate of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. So basically, if I were to rewrite this, I would say the rate of gas 1 all over the rate of gas 2 is equal to the square root of the molar mass of gas 2 all over the square root of molar mass of gas 1. Now, this seems simple enough, but one thing I would like you to be aware of is I want you to note the difference, oopsie, not B. Note the difference between rate versus time. So in this case, you can think of it like this. Rate and time are inversely related. As the time goes up, the rate is slower. All right, if the time goes down, the rate is faster. You can think of it like this. The faster you get to a destination, the less time it takes, the faster your speed. Or the longer time it takes, the slower your speed. Okay, now, when you take a look at your textbook, I believe it's on page 217. Okay, so if you take a look on page 217, they talk on page 219, they talk about effusion and diffusion. And what they do is they give you a sample in terms of the calculation. In this particular case, they give you the rate. So in this case, they show you how to set up the equation, do the square root, and you get your result. Okay? Now, they do the exact same thing in terms of diffusion here in the calculations. All right? So something for you to be aware of is to take a look at the examples on page 220 and 219. Now, they talk about this ammonia and hydrochloric acid, and you'll see this little diagram on page 221. What I will do is I'll put a link to a video that actually shows this particular experiment just to prove that the different size molecules have a different size, different speeds. Okay. Now, the other thing is this, kinetic molecular theory and gases. Not all particles have the same amount of energy. Therefore, do not travel at the same speed. Some travel slower have less energy while others travel faster. If we were to take all the particles and we were to take a look at their speed, what we would get is something called a Maxwell-Boltzmann distribution curve, which represents the energy distribution of particles at different temperatures. Now, a way you could think about this would be like AKA bell-shaped curve. Now, for a bell-shaped curve, what happens here is this would be higher energy, and these ones would have lower energy. Okay, and what happens is this peak here, this is the energy of the majority of particles. Okay, now, so an example of bell-shaped curve would be like your class results. Some of you with a higher energy would be like those students with higher grades. Not all of you have higher grades. Not all of you are getting 90%. Conversely, lower energy would be like not a lot of you are getting like 10% in the class. The energy of the majority of the particles would be like the class average. Now, in this particular diagram, you see that there's a green line and there's a blue line. Notice the blue line is a little bit more distributed, and notice the peak of the blue line is a little bit further along than those of the green line. So in this case, the blue line, or the line with T equals 350K line, 50K line, that means have a higher average energy. And that's why it's distributed a little bit further along. So when you take a look at a Boltzmann distribution curve or a bell-shaped curve, the further along the curve, the further along that the peak, that means on average, the particles have higher average energy. Okay. Now, because particles, many different particles are moving at different speeds, and generally we can only get the average speed or kinetic energy of all gas particles can be calculated by this formula. Ke is equal to half mv squared, or Ke equals half mu squared. Now, some of you may have seen this in physics, but mass would be in kilograms, while v would be the velocity of the particle or the average velocity. Now, a lot of times we use the average velocity used for gases. And the reason why we use the average velocity is because, again, because of the Boltzmann distribution curve, some particles are moving slower, some particles are moving faster. So the best guess that we can do is using the energy of the majority of particles or their average energy. Okay, now the relationship between kinetic energy and temperature for a gas is given by the following equation. Kinetic energy is equal to 3/2 R, which is the universal gas constant, divided by T. Now, notice there's kinetic energy here, kinetic energy here. What we can do is we can combine the two equations And so we get the average velocity is equal to 3 RT divided by the mass square rooted. So URMS is the root mean square velocity or the average velocity. R is the universal gas constant, and mass of 1 mole of the particles in kilograms, aka molar mass. Now, again, because the gas particles move at different speeds and directions, the root mean square velocity is used to find a single velocity value for all the particles. And using this formula, one can now understand why processes such as diffusion occur at a slower rate for liquids when compared to gases, or if the molecules are heavier. So again, what happens is the heavier the particle, the slower it is. Why? Because in this case, the larger the mass, in this case, if we do U is equal to 3 RT over the mass square rooted, the bigger the mass, the bigger the denominator, what happens is you get a smaller value. Okay? Now, this is also described on page 217. If we look at the very top here, they talk about the root mean square velocity. Okay? Now, the one thing is that you don't need to memorize these formulas. They will be given to you, but what I want you to do is, are you able to apply the concepts? If I were to give you this graph and say, explain to me, why is oxygen have a lower average speed than, let's say, helium? You need to be able to explain to me, because of the fact that, because in this formula where the average velocity is dependent on the mass of a particle, the bigger the mass, the slower the particle. Okay, so that's why in this particular case, I'm not going through many equations for you or going through sample calculations. The sample calculations you can read through your textbook, but the idea I want you to be able to understand is how to apply some of the formulas. What do the formulas mean? All right, folks, thank you very much. Have a good day. Bye-bye.